Well, you might notice that this is a little bit different than the last lecture I just gave, and that's because I was asked to leave the building right there. So now we're on a much smaller screen. Hopefully you can read this right here. So last time I went through ropes, but now this time I want to go through friction. Now we already had our last three forces right here. The weight, which was mg down, the normal perpendicular surface through the object, and the tension parallel to the rope and away from the object. But now we're going to have a frictional force right here. All of our frictional forces will be surface forces. We're not going to deal with air friction. These are all frictional surfaces, the friction between two surfaces. And we're going to use the label FF right here to designate the frictional force. And the direction is always going to be parallel to the surface right here. Now, parallel to the surface still leaves two possibilities. If we look at this block right here, and this block is being pulled that way, then the frictional force is in this direction. And you could say, well, it just fights, fights the motion right here. If the block is moving this way, the friction is in that direction. But you really can't use that one because over here I have a car and it accelerates off to the right. And we say, what force propels the car to the right? And the force that propels that car to the right is the frictional force. If you had no friction on the bottom of the tires, they would just sit there and spin. So you need friction on the bottom of the tires. And you say, which way is the frictional force on the bottom? The frictional force is not in this direction. The frictional force is actually in the forward direction. So it's actually going over here like this. The reason why it goes that way is because the tires are trying to spin around and the friction is what's fighting that slipping going on right here. So the definition of friction, the best way I see it is that it's parallel to the surface and fights the slippage. So over here, the tire wants to slip this way, the friction is in that direction right here. Here, the block wants to slip that way, the friction is in that direction. That will always give you the correct direction. Now we have to look at friction for a minute. Suppose we come along here and we pull on this and we plot out that tension versus that frictional force right there. Well, if I just barely pull on this block does not move. If this block is not moving, then these two forces should balance right here. Matter of fact, as long as this block doesn't move, these two forces should be equal because there's no acceleration on this. These two counteract each other. So down here, I was slowly pulling this greater and greater, the tension, and as long as this block's not moving, these two are equal to each other. If these two are equal to each other, that's just the y equal x line right there. This term equals that term. And this is going to happen as long as this block isn't moving, and we call that the static case right here. Now, eventually this thing's going to slip, but the maximum you can pull on that and not have it slip would be the maximum static friction right here, right there. That's the maximum it can be. Okay, and we'll call that the frictional force maximum static right here. And it just so happens that that is dependent on the normal. It's proportional to the normal force, the same normal force that we have for that surface. And so if we're going to say it's proportional, that must mean it's equal to some constant. There's a constant times the normal. We call that constant the coefficient of static friction. There is no units on this number. There's no units. It's like 5 or 6 or 0. If mu, we call it mu s, if mu s is 0, then it's smooth right here. If we wanted to look at something like rubber on asphalt, it depends on the two surfaces. Mu is 1. And if it was wet, it might even be a little bit different right there. It would be a little less than 1. Your book gives you a whole table of these mu sub s's. There should be a little s down there. Okay. Now, that's only for this point right here. But all these other cases right here, that's the true friction. That was only on the verge of slipping. So in general, the friction is below or less than or equal to that. It's down in here. So the frictional force static is less than or equal to mu Sn. And this is empirical relation right here between the friction and the normal. And many times I will say that you're on the verge of slipping. That means this becomes equal. So if you're on the verge of slipping, this becomes equal. But in general, it's less than or equal to. Okay, so that takes care in the static case. Now, if I pull a little harder, it starts to slip. When it slips, the force required to pull it gets cut almost in half right here. It jumps down to you discontinuously right here. And if I pull harder and harder, the force, this doesn't change at all right here, the frictional force. So this, we call this the kinetic friction. It's slipping, it's moving. So we usually use a little K for that. And since it doesn't go uphill, there's no slope to it, the frictional force is equal to mu Kn, where mu K is the coefficient of kinetic friction. Again, it has no units. They give you a table of it in the book. And in mu K is always less than mu S. It's usually somewhere about 50% of the two right there. So these are the two cases we have. The case where we're slipping, which is this one down here. The K is for slipping. The S means static or not slipping right there. So don't get those two confused. Okay, so now let's come down to here and let's put some friction in. So here, this is not smooth. There's some friction in there. And suppose we say, what's given these two masses, what should the static friction, mu S, the coefficient of static friction, be so that it's right on the verge of slipping right here? You know right now if mu S is 0, it would slip. Mu S were huge, it would slip. What is the smallest mu S can be and still not have it slip? So we go ahead and we draw the forces. We got the M1G, we got the normal going up, we got the tension going that way, but now we have friction. It's trying to slip this way, it always fights the slippage, so it's coming back. This would be a static friction because this is not moving. Over here, we have the M2G and we have the tension. So what we want to do is write out the forces. After we draw the picture, put the coordinate system in, now we draw the forces. On this block, what do we have? We have T minus friction equals 0 right there because A is 0. This is the static case. Then we can look at the forces in the Y. We have N minus M1G, and that also equals 0. There's no acceleration here. Over on this point, we have M2G. Remember, we don't want your two coordinate systems fighting each other, so we're going to call both these two directions positive. M2G minus T equals 0 because this is not moving too, right here. If that's not moving, that one's not moving. And then we have one last thing. Since we know we're on the verge of slipping, the friction is equal to mu Sn, the same formula we have up here. But when you're on the verge of slipping, it becomes equal. Okay, so from these three equations, I said, well, let's take these two equations and just add them. If we add them, the T's drop out, and we just get the M2G from here minus the friction equals 0, adding these two. Well, I'll put in what the friction is from right here. That's just mu Sn. And we'll put in what N is from right here. N is just M1G. So we can put in M1G. And so now I can just cancel the G's from both sides and divide out the M1. So mu S is just M2 over M1. So that's what we wanted to find. That's the minimum roughness of the surface. If the surface were any smoother than that, it would move right here. That's what that's telling me. So now let's look at the other case, the case where we're actually slipping right here. And this time we'll say we're given the two masses, but now let's say we are given the roughness of the surface when you're slipping, mu K. And we'll find the acceleration and the tension in this string right here. Well, the equations are very similar to these, almost identical, except now everything's accelerating. So they're not equal to 0. So this first equation used to be T minus friction equals 0. Now it's T minus friction equals M1A. The second equation, that's exactly the same. N minus M1G equals 0. The third equation is going to be the same, except we have an m2g minus t equals 0. Now it's m2g minus t equals m2a. So here are my equations, plus we have our frictional force equation, which is mu kn, which I threw out over here. Now, we'll again add these two equations together. The t's drop out, and we get m2g minus friction equals, and then I factor the a out of these two, a times m1 plus m2. I'll put in what the friction is. It's mu kn. That's all I did right there. And the next line down, I'll put in what n is. N is m1g. Put it into here. And then bring this over to the other side. And I factored out the g. So a equals g m2 minus mu k m1 over m1 plus m2. So that is the acceleration right there, given a certain roughness such that it did move right here. Now, if I wanted to solve for the tension, I would take that A and plug it into either this equation or this one, doesn't matter, and solve for the T right here. Now, I imagine by looking at the picture right here, just by thinking about it, since if I cut the rope right there, this thing would accelerate down at G. I know this is accelerating down at less than G, because I can see right here you're subtracting over something added. A is less than G. And I know this block isn't going upward right here, so I know that the tension better be less than m2g. And over here, since this is accelerating this way, I know that T better be bigger than the frictional force too. So one way to check the answer is when you solve for T, see if it's less, it should be less than m2g, and it should be more than the frictional force. Remember, the frictional force is mu k n, and n is m1g. So you know that when you solve for the tension, it should be in that range, because it slows this one down, it sped that one up. That's what the two tensions did. Okay, and so I think when we're dealing with friction, we've got to sometimes look at it for both the static case, the one where it's not moving, and the other case where it is moving, the kinetic case, the slipping case right here. Okay, so that'll be our only 4 forces we'll use for the next 2 assignments. You have assignment 4 and 5, but this is all you need to, I think you know everything possible to finish up assignment 4. The next talk I give will say stuff about section 5 right there.